I have another volume by slicing problem for us. And here's what it's saying. Okay, we have this log here, and it's in the shape of a cylinder. And we have a half a log, so we have a half a cylinder, really. But that cylinder has a radius of 1, and this log here has a height of 5. So what we do is we take this log, and then we pick up an axe, and we chop out a piece of it, and we chop on this line. We're pretty precise. We chop on this line, z is equal to 2x. And we end up with this wedge over here, which I've drawn. And what we want to do is find the volume of this wedge that we chopped out of this log. So again, this is a volume by slicing problem. Why don't you pause the video and work on this problem? All right. Assuming that you've given it a go. Again, we said this is a volume by slicing problem. And the main order of business that we need to find is how we're going to slice this wedge up. And then how can we find the dimensions of that slice, find the area of that slice, multiply it by a little differential to get some little differential of volume, and then we want to sum up all of those little chunks of volume to get our total volume. That's the main objective here. And what I have graphed out is kind of three-dimensionally what we're talking about, and then over here is our top view, and this should be -1. But again, this depicts our half of a circle here of radius 1. And the last piece of information that we need to draw out is how we're chopping this. So z is equal to 2x. If we were to take our eyes, and look at our log from this point of view here, this angle, we would see the following. We would see the positive x-axis, and we would also see the positive z-axis. And then all we need to do is plot this line here. Z is equal to 2x. So we have 1, 2 over 1. Okay. And then another 1, 2 over 1. So we get a line that looks something like this. Something like this. So this is z is equal to 2x. And that is what we're chopping along with our axe. And so we call this our side view real quick. But again, this is all the information that we were given. And now we need to figure out, okay, how can we slice up this wedge here? I think that looks like a Choco Taco. I don't know about you. But how can we slice this up in order to start talking about, okay, we want to sum up all these little pieces of volume in order to get the total volume. And to me, I think the best way to slice this is going to be something like this, where we take these triangular slices here. Okay, get these triangular slices. These are going to be right triangles. And when we sum these up, drawing out another slice would look something like this. And again, you can see these are different triangles. These are going to have different sizes here, but they're both going to be right triangles. And we know that they're going to be proportional. And that's huge. And how do we know that? Well, because we're slicing along this line here. So they're going to be proportional to the slope of this line. And I graphed a little too much here. We're told that our circle only has a radius of 1. So our line is only going to go out to 1. Only going to go out to 1 here. And we're going to get this right triangle you can see. So that's going to be the largest right triangle that we see. And as we go along, we're just going to get similar right triangles. We're going to get similar right triangles. So we'll be summing up all of these, but they'll be proportional off of this slope. So we know that this full length here is going to be x, okay? And then this height is going to be 2x. So they're all going to be related. They're all going to be similar triangles. And this is huge. So if I were to take one of these out, if I were to take one of these slices out and sketch that, we'll sketch that. Get one of these going. Something like that. Okay. Something like that. Get that going. All right. So that's one of our slices with a little piece of depth. And what we found was this. We found that this length here is going to be x, and then this height of our triangle is going to be 2x. We still don't know the depth, but we'll figure that out shortly. But right now, what's cool is that we can figure out what the area of our slice is going to be. The area of our slices. And that is going to be the area of this triangle. So the area is 1/2 base times height, which is going to be x times 2x. So we're left with our area is going to be, these 1/2 and 2 are going to go to 1, and then we have an x squared. We have an x squared. So that is the area of one of our slices, this right triangle here. And lastly, again, because we want to ultimately set up what? We want to set up a definite integral. A definite integral, summing up all of these chunks of volume here. Right now we have area, so we need to multiply our area by some differential to get our little chunk of volume here. So what is going to be that differential? And we're going to find that by looking at our top view. Our top view, our slices are going to look like this. Our triangles are going to look like this from our top view. And are we going to want to sum up all of these slices in the x or y direction? Well, we're going to want to do that in the y direction. We're going to want to do that in the y direction. So this is going to be a little dy. We're going to be summing up all these slices in the y direction. So our depth we find to be dy. So now we can start to put together a definite integral. So I'm going to write that over here. We can now put together our definite integral. We said our area is going to be x squared. The area of our triangle is going to be x squared, area of one of our slices. And then to get some volume, we're going to multiply that by a little piece of y, a little dy. And now we need to figure out, okay, what do we have here? We're integrating with respect to y, but our integrand is in terms of x. We need to fix that. We need to get this in terms of y. And we can do that. We have the equation for our semicircle here. And again, this is a semicircle. We're having x be greater than or equal to 0. So we're only interested in positive x values. But again, if we were to solve for, we want to get this, we want to solve for x squared and have everything in terms of y. So this is going to be 1 minus y squared. X squared is equal to 1 minus y squared. So now what we can do is substitute this in, and we should be all set then. So we have the integral of, and this will be a definite integral. We'll fill in the limits in a little bit. We'll have the definite integral of, now we're going to have 1 minus y squared, okay? And then we are going to be, again, integrating with respect to y. So this is still dy. And now we need to figure out the limits of integration. What is y going to be? Where are we summing up all of these slices here? Well, we're going to be doing that from -1 to 1 in the y direction. But one thing to notice is, could we use symmetry? Symmetry always helps us in evaluating these definite integrals, so let's try to use it. We could go -1 to 1. Or we could go 2 times this integral, where we use some symmetry, 2 times, and we go from 0 to 1. This is just using some symmetry, and will help simplify our evaluation of this definite integral a little bit. So now all we need to do is evaluate this. So we're going to get the following. Anti-differentiating, we are going to be left with 2 times y minus y cubed over 3. And then we are going to be evaluating this at 1 and 0. 1 and 0. Okay, and let's see what we get. So evaluating this, we're going to have 1 minus 1/3. And then at 0, this whole thing becomes 0. So we'll just have this here. And multiplying by 2. So 1 minus 1/3. 1 minus 1/3 is 2/3. So it's 2 times 2/3. And this is what? This is 4/3. So this is our answer here. We have made it. We have found our answer to be 4/3. So this volume of this little wedge that we chopped out, this Choco Taco looking thing, is actually 4/3. Our volume is 4/3. And we're done.